computing.
Okay. Hello, everybody.
Hello. So my name is Nicolas.
And I'm Urmas.
And today we'll present you the Space HPC, which is ESA's HPC. So ESA, let's start with acronyms. ESA is a European Space Agency, and HPC means high performance computing. We'll start with the general idea of what is an HPC, and then we'll go specifically on the Space HPC. So an HPC, it's not the common word to design an HPC would be to say a supercomputer, but it's not really conveying really the reality of an HPC, because it's not one single computer. It's a gathering of several small computers that are all interconnected, forming the HPC system, so a high-performance computing system. And yeah, that's it. It's really you don't scale up a big computer. You scale out using several big or relative mid computer to have a big computational power. So if you want to use an HPC, as it's made of several individual computers, you need to understand parallel processing, and your workload, what you will run on an HPC, need to be parallelized to effectively use all these individual computers. And we have on an HPC specialized hardware, so each of the individual computers can have either CPU or a GPU. It is quite used now in AI and machine learning workloads. Small also thing on the who is using an HPC. It's been mainly used until now for scientific research and academia. European Union is funding a lot of projects which is called Euro HPC, and they are doing this so that each European university and research entity can have access to high-performance computing resources. But we also have engineering companies using HPC. For example, last year, Eni, the oil and petrol and energy company in Italy, has built the second fastest and most powerful HPC in Europe. And last example, before going on with the Space HPC, ECMWF, which is the European Center for Medium-Range Weather Forecast, has several HPC so that they can predict the weather in Europe. How do we use an HPC? Here I show you the difference between running on the cloud and running on an HPC. So maybe some people are familiar with, on the left side, how it goes on the cloud. So you go to your cloud provider, AWS, you get a virtual machine with fixed resources. You own the machine, and you can run your processing anytime you want. Like I took this example of an orbital simulation, and you run it. On an HPC, it's quite different. It's you are inside all the individual computers are inside the resource pool that is shared by all the users. So you need to be granted access to the resource pool and to ask to have access to the resources. And it goes really, you ask for resources only when you need them. And I wrote, as you can see in the pseudocode, you need to say, I need that much resources for that much time, and you submit we call it submission of the workload. You submit this to the HPC, and there is a scheduler handling all the requests for all the users, and you get into a queue, and at some point your job will start when there is some resources available. Now on the HPC, so it's ESA's new supercomputer, but it's also mainly it's the first one. So as it's the first one, we built it as a technology demonstrator. It's not something we're not sure yet it will be forever. So we made it into a modular design, which was fast to build. You can see on the picture, it's several containers. We have one container for the power, one container with all the racks, all the servers. One part is also the cooling. So it was quick to build. We started building it last year, and it got inaugurated in March this year. And like this, also the modular system, the idea is if we want to grow, it's only a beton slab with several containers, so we can add some components on the slab. We're not constrained by building issues. On the use cases, it can be anything of space industry, like mechanics, fluid dynamics, and we expect a lot of AI. We have some machine learning, of course, workloads. Important question, for whom is the Space HPC? The first people we started working with was ESA internal people, because we have ESA is not doing. Not everyone in ESA is doing technical work, but some are, and they were missing some HPC resources. And we started with them because it's easier in terms of security to onboard them. And now we also have industry, that any industry that has a contract with ESA can be granted access to this Space HPC. They only need to be sponsored by their contact in ESA, and they get access to the Space HPC. And the last one, they are still not yet on the Space HPC, but it's planned. Actually, it's one of the big reasons why the Space HPC was built, is to give access to startups and small and medium enterprise in the space industry. And maybe we can do a small poll. Is anyone in one of these situations, in the second or the third? Does anyone can have access? Okay, so don't hesitate to contact us. Either you have a contract with ESA or you are supported by ESA in some way, either through incubators or the commercialization initiatives. So don't hesitate to ask us. Yeah, so as I said, we built the Space HPC because we identified a gap in HPC. As I said, HPC, it's mainly used traditionally for research and academia. So if you are a startup or SME, you cannot be granted access to this fancy Euro HPC because it's only for research. It's not for research and development. So if you're a company, your only choice is to go to public cloud, AWS, and it costs a lot and can really be a drawback, so an issue for you for innovation. So the Space HPC, the main goal, it's not to provide ESA people HPC resources, it's to provide space industry HPC resources. And the key benefit, for now it is free for anyone to use, that is eligible to have access to the Space HPC. The decision to extend this no-cost access will be taken shortly. We expect it at the end of November. But for now, it's until end of 25, no-cost access. And we made it, we don't want to put too much of a burden for people to ask for HPC access. So we made it into a light application process and something relatively quick. We don't wait for 6 months to get access to the Space HPC. On the technology, we have some of the state-of-the-art from last year or from 2 years ago hardware, so in terms of CPU and GPU. And then, of course, high-speed network, because as I told you, it's individual computers working together, so that they work together effectively, you need a high-speed network. And Space HPC, we've submitted our results to the top 500, which is the top 500 of the supercomputers in the world. We placed 261st in the rankings. So it's let's say we are not part of the biggest HPC in the world, of course, but as we are using some of the most advanced GPUs and CPUs, we are quite energy efficient, and we are 59th in the green 500, even though we are quite small. So in the green 500 is the energy efficiency ranking. So with the same compute power, we will spend less watts, not too many watts, not too many power, not too much power. And so I told you about the hardware. This is the general case. On the Space HPC, we have NVIDIA 800 in terms of GPU, and AMD EPIC, the last generation in terms of CPU. It's the two main components of the Space HPC that enables you to run computations, but they are really different on what they can do. GPU, they are really good at parallelizing the same task and doing, for example, matrix computations, processing of images, and deep learning, but they cannot do everything. The CPU is much more versatile, but if you run the same task on GPU compared to CPU, you will have a much better energy efficiency on the GPU. Like the order of magnitude is like around 5 to 10 more efficient on the GPU. And the Space HPC specifications, here is the details. So with this, we are 261st in the top 500. We have 150 nodes. So one node is one of the individual computers I was talking about before. Each one has 192 cores. This is only CPU, so you can redo let's say old school traditional fluid dynamics or simulation on it. Then we have two partitions. We call it partitions, these different nodes. We have the accelerated, the orange one, that have on each individual node that have 4 GPUs. And then we have what we call AI partition. On each node, we have 8 GPUs. So it's similar, it's the same kind of GPU, 800, but AI is still, one single node is 2 times more powerful than the GPU one. And then a bit more, we don't have so many of visualization node because it's not a workload we expect to run a lot. It's for anyone that needs graphical workload to be run on the Space HPC. And the last one is FAT. So it's the same CPU, the same as the CPU node, but with a big memory for some people who need simulation that cannot parallelize across several nodes and that need one node with a lot of RAM.
Okay, so I'll take also a moment then to talk about a bit about the parallelization and how this then practically looks like. Just a few more words. I mean, this is a general information, but what we'll also then talk about is a bit about the software and how to build these things in general, and this is what I will just shortly discuss, but we'll also do a demo at one point, so you can see how it actually looks like as well. So the HPC is a nice thing, but in order to get any value out of it, you actually have to do something with it. And building this software, well, first you need a use case, which is difficult to find in some cases, but if you find one, then you also need to optimize the code and how you run this. And compared to the regular, let's say, software that runs, it usually runs on a single thread, so it just runs from start to finish, and it's not very optimal if you want to run something that lasts, well, that needs a lot of resources or runs a long time. And this is what this graph tries to show you, that there is a process that runs X hours, and you just try to fill it out. For myself, I've explained this, or I think this is the easiest way to explain this, is that if you imagine something like a stupid sort, this is a sorting algorithm that you have like numbers 1 to 6, and you randomize. And the winning condition, or when you have sorted, is when you have 1 to 6, all aligned, right? And if you start running this on this process, then it will take you forever, because every time it needs to calculate, right? There is no way to create kind of boxes and try to then, resort this or somehow do it smartly. But if you now, if you now have multiple cores, multiple ways of calculating this, then instead of doing the calculation on just one, you can split this half and then do it in parallel manner. So this is how you optimize this. You can imagine having a huge task, and instead of trying to solve this in one thread, you just split this up into multiple threads, and then you have half and half and half, and until you have like optimally optimize this, that you get the result extremely quickly. And this is why the HPC is good, because you have the possibility to schedule these types of jobs into different threads if you build your software correctly. and then you can have a major time win when you do this. This said, when you build a software for the HPC, right, you need to use something like OpenMPI or something like that, which already has this inbuilt ways of threading and calculating, or not calculating, but actually communicating with each other and helping to build this smart way of calculating results. There's also the aspect that this is ideal world, right? When you actually do calculations, and if you actually build software, then there is still dependencies on what you do. So you imagine doing these kind of calculations, but you need to store the information at one point. So you have a stop because you need to store it. You need to stop this maybe, and then get the results from one other node and to start another node. So there is certain limitations in how you build this. But nevertheless, when you build software for the HPC, if you want to actually use the HPC efficiently, then this is the way you need to go. Again, being Estonian myself, I know there is not that many companies here that actually would use HPC in many cases. But this is also because there has not been an opportunity to do so. So if you have the opportunity, it just also needs you to consider the processes and how you build things a bit differently. But threading is the core principle behind this, or this multiprocessing. And this is illustrated also here, right? Because it's not just, as I said, it's not just every node or every calculation does not work in a box on its own, although it can. It still needs quite often to communicate each other. So you need to also consider that when you do something, that how you actually transfer the information, how you store it, and what is the inputs and outputs for these different boxes that you want to calculate this. And this also, of course, adds to the execution time, because every time you start messaging between different processes, then it is something that creates wait time. So all in all, what this means is that the software that you build is different than what you would usually build. So the HPC software is quite often something that you need to actually plan the architecture for. So it's not this regular one that you usually do. The OpenMPI, which is usually used, right? This is it's not complicated to do, but it's just something that you need to prepare yourself for, or when you try to already think about things, especially for the architecture and what you try to achieve as a use case, then you need to consider that this is something that would optimize everything that you do. So it's just something that architecturally you should consider or think about beforehand. Then, for the, I guess we go also for the demo soon, but just this much maybe, that what Space HPC, or what this HPC uses, is called something that PBS. This is a portable batch system. So different HPCs use different software, well, let's say based like operating system, let's put it this way, to run these processes. There is Scrum, which is quite, Slurm, sorry, not Scrum. Slurm. Slurm is quite often used, which is like an open source version of this kind of HPC software. Space HPC uses something like PBS. They have different syntaxes and different ways of starting these kind of processes and stopping them. But at the end, when you build a software, it doesn't matter. Software is software that you build. You just how you initiate it and how you connect it is something that we also demonstrate to you. Do I also talk about the queues myself, or do we?
I think we go through them.
Because we're about to get to the demos, but just this much maybe, that the space, well, in general HPCs, they use something called queues. So every time you want to run something, it's placed into a queue, right? You can imagine having a queue, and there are different priorities, and this is where the different syntaxes of the workload manager, or the software that then runs this, come into play. So PBS is a bit different. It's not complicated. But it's a bit different. Let's put it this way than Slurm. So I guess it's easier. I guess when we show a demo, or we just discuss about this as well. I guess a bit.
You can explain
the architecture a bit. Yeah.
Yeah, that's the big picture of the Space HPC. It's a bit complicated, but what I would like you to remember of this drawing is that we have two fast networks. That is only the internal network of the HPC. We have the orange one that is only for the storage, so for handling all the file system operations. And then the green one, which is only for inter-nodes communication. So as I said, the nodes need to communicate among themselves so that they can effectively tackle a big problem. And this green network is made for it. And we separated really this communication network with the storage network. And the rest, not too much to say, except as you saw in the previous drawing, that users don't have access directly to the compute nodes. They only end up on what we call login nodes that are not really the HPC, it's only a front door. And to get access to the compute nodes, you can only go through the scheduler, the PBS that Urmas talked about.
I'll go back one moment for this picture before we go forward. As they said, the login node. So as an end user, what you would see is just a Linux machine at the end with Linux commands. You would need to write bash scripts to run your program. So you would need to build the program as well. The program then is usually built either from Python, C. So there's many options. There are many options, but I guess Python is something that is quite easy. And you would never see the compute nodes, right? You would just use you see a Linux terminal where you can use certain commands to submit a job, and then you would get a result. You would not even know about the queues necessarily, how the queues work, but in the background, there is a bit of clever magicry behind this to make sure that all the jobs fill the resources in the most optimal manner. This is called what's it called? Anyways, so there is a queues behind. there's queues behind with there are different types of queues, but it tries to optimize the resource usage, and for the end users, you would not notice this. And yeah, And then you also have, of course, the file system where you then can store the results.
Okay, I will explain you what the demo is about. Something I didn't mention is that the Space HPC is located in ESA site in Italy, in Esrin, which is located in Frascati. And there it's really the heart of the Earth observation program of ESA. So let's say that we get a bit of influence from Earth observation. So our use case will be on Earth observation, and we have to say that quite a big proportion of our internal users of ESA are from this field of Earth observation. So it's the use case is something quite traditional in Earth observation, which is you have a satellite with a sensor red, blue, red, green, blue, and near infrared, doing acquisition over the globe. And with this sensor, you get two outputs. One is RGB near infrared image, and with the same sensor, you can also capture more light, but on all the 4 bands. You can aggregate the 4 bands, so you get a higher spatial resolution, but you get it in black and white. So that's really the raw output of several kinds of satellite, like Spot, or Sentinel is not working like this, but Spot, for example. And what we will process in our demo is what we call pan sharpening, which is merging these 2 images, so the color one with the black and white, so we can get the higher resolution image in color. And how are we going to do things? It's always the same with HPC. You really need to parallelize your processing. You need to split your big problem into smaller problem. And we can say really that in Earth observation, it's relatively easy to do so because you have a big image, satellite images. The Spot one, for example, are like 40,000 pixels times 40,000 pixels. And we can simply split our images in small tiles and run the same processing independently because each tile doesn't interfere with the other tile. So yeah, that's why we can really easily do Earth observation processing on the HPC. And you have a few examples of libraries in Python. You can use Dask. Then you have Orfeo Toolbox that is really specialized for satellite image processing, or any custom code that will split your image in several tiles. Now a bit of the code that we will use to submit our job. This is a PBS script that Urmas told about. And this is the syntax that we use to request resources to the HPC. So it's the first syntax is the $PBS. And here we say select one node with one CPU and one MPI process on it. And we say, I want it for 30 minutes. You specify that it will run on the CPU and with a job name, and then is the actual script in what you will run on the HPC. But first, you need to ask to the scheduler how much and for how long you will need. I will show you then after live on the demo how it looks like.
Maybe this much more that what happens then after this is submitted, then it goes to a scheduler. This is the core principle behind the HPC, that there is a scheduler, and this now takes all these jobs, lists them. What I tried to say before, it was called fair share. So everybody has a certain amount of resources that they want to use, and scheduler's job is then to figure out what job should run. right? Depending on exactly on the wall time, how many CPUs you want to use. So it then tries to decide and make this kind of nice queue and run this in a correct manner. And then there is of course different other principles there, which maybe we not should go into, but like a backfilling and then the priorities. So when there is a priority job, what happens, and so on and so on. For end users, usually it doesn't matter, but just so you know that there is in the background, there is a queuing and scheduler that actually manages and does all the jobs. Well, it lists the jobs and then runs and gives you the results. So maybe we'll take a short break then, and then we'll do a demo.
We will prepare and
like 10-15 minutes, and then we'll show you how it actually works.
Hear the ocean's loud, and now your favorite station's fading out. Ooh, but since you're not around, it's not a conversation I'm about. Your laughing helps me out each time I start to float away. play guitar and drown. Oh well, your favorite station's playing loud. Ooh, just saw the greatest clouds, but nothing moves me when you're not around. Your loving helps me out each time I start to float away.
don't know if okay. I guess we can continue. So we've discovered an interesting bug, not a bug, but a feature, that we scheduled a job for this demo, but there is a time difference, so nobody calculated for the time difference. But it's fine. It's fine. Nicolas managed to do some magic, so he can do the demo.
It's okay, yeah.
But lessons learned. We do live in different time zones, so yes.
So what we'll do with on this demo is really put illustrating what Urmas showed with when you parallelize a task, the ideal case makes it speed up. If you have 100 CPU, it will be 100 times faster than on one CPU. But we will show that it's not really the case. And what we want to try is compute this kind of graph, which is the ideal speed up in red, and what we will actually get from our experimentations is the blue line and the real speed up. Let's log in. I hope no one is afraid of command line interface, because I mean the reality of using an HPC is you do almost everything via command line. We also have a web interface, but it's really not convenient, and I don't know anyone using it. So we'll do everything with the command line. You see the screen? Is it okay?
Maybe before we do this start, maybe we also take the questions now, or we do
yeah,
later.
we can.
So maybe it's easier if you have any questions beforehand. Maybe then it's easier to take them now, because after demo you may have completely different questions. Yes.
I have a question. You have to allocate time. How can you know in advance how much time you need?
Yeah, the first time you run your job, you don't know exactly how much you will need, so you will ask for 24 hours, see how long it takes actually. Let's say it takes 2 hours. So the next time, the next run, you can ask for 2 hours. It takes a bit of try and trials, experiments to get to the real.
I think that's the key, yes. It's a bit of trial and error. Especially if you haven't done this before, you will try to first, I mean, it's anyways, you need to build a script, you need to optimize, so it's a bit of a trial and error. Yes?
Yeah, you can use both. Either you compile really on the HPC hardware, like this you are the most optimized, you know it will run fine. But I mean, people also use precompiled. You can use containers also on the HPC, which is the most convenient way. And really, you don't bother with compiling on the HPC. Usually, if people want to go fast, we say just bring your container in the HPC and run in the container. Exactly, yeah. Currently, I mean, we started with external users only a few weeks ago, so it's not very big. And as I told you, we didn't onboard startups yet. So we have some. I can show you currently what is the usage of the HPC. So the command is qstat. It's to get the stat of the queues, and with n, I can also show which nodes are used by which job. So here we see one job, one big job. Maybe I will do it without.
I guess the general answer is that it's fine right now, but
Yes.
there is a list. There is a list. So there is a list of people who would like to use it, but
So we see that currently only 2 jobs are running, one big and one small, and only on CPU. No one is using the GPU. So that's the basic command to check how your jobs are going. You can see them in the queue, see if they are running or still waiting. So let's get to the job. Here it's our PBS script to request resources and to run the job. We've made it into a template, and we will just change the number of nodes, the number of cores. So the same, this template we will run in several times, just changing this number of nodes and number of codes. We use MPI. This is a famous library for communication between jobs. And the last command, we don't run directly our Python script. We've wrapped it into MPI run, so that this Python script is run across several nodes, and everything is coordinated by MPI. And we use a countdown environment on this one. So I mean, you see, you can use really anything on this HPC directly. Countdown like you would do on your personal laptop. Okay. Now, maybe we can just have a quick look at the script that we will run, the Python script. So first we need to define what is our individual process that we will run. We have splitted our images. I told you we split our images. We did it kind of manually. And we will run this function, process image, on each of the image, each of the tiles individually. And the main function is this one, PySharpen. And that's here the core processing. And then the orchestration is done right after with some MPI stuff. So this script is run, let's say, 100 number of times. And maybe Urmas, you can explain with the rank and the size.
I mean, I don't know how many technical people there are here. So, as I said, I mean, what is important, I think, I'm not going to go into all of these, I guess, details, but the important thing is that this function, this thing that runs in the background and does all the magic, these functions can communicate with each other, right? So that is what is in principle happening. So you set up the communication or this pipeline to actually communicate with each other. And yeah, I mean, yeah, it's code. So let's not, I think, go too deep into.
It's really some MPI logics to distribute the works, and so that each individual worker gets a piece of the big job to do, and individually process a small part of the problem. And then at the end, we just summarize everything. And once each of the individual workers are done, we declare the process to be finished.
One thing, I guess, is that usually these type of code, these are not very long. These are not very, I mean, complicated. So it's again a bit different. They don't have this kind of usually visualization afterwards. So again, it's more about the business purpose of what you try to achieve. So you have to really figure out, and then you actually do something with the results. So this is more of this background work that you do beforehand.
Okay, so let's start. We we have this function to submit jobs. So it's all a wrapper of the template job I showed you to replace the number of nodes and the number of cores on each node we will use. So we'll start with the basic one, single node, single cores. And we can check now if it's running. I just print for only me. We can see that it's running on the node that is called CPU1. So once the job is running, I can get SSH access to the node. And we can check how it's going. Well, we can see that our job is running. We see it's only one CPU core indeed, 95, 96%. So it will take a long time. I think in my experience it's about 20 minutes on this single core. So let's continue to submit more jobs. We'll do the double 4 times, 8 times. We'll do a few. Okay, that's already a good start. So for now, we're still only on one single node, nothing spreading across nodes. Oh, sorry. And we can see our jobs are running, and we see 1.1 is one node, one core, 1.2 is one node, 2 cores, and we can see all our jobs currently running. And if we have a look, for example, to the one running on 8 cores, I think it's already finished. So here I'm connected to the node that is running on 8 processes, and we see exactly 8 processes running on this node. And still using also 97% of one single CPU. So I believe this one will be quite scaled. It will be a good scaling, which means it will run almost 8 times faster than the single node. Let's go on with submitting jobs. We have 190 cores on each node, so we'll try this limit. So that's the max we can do on one single node. Then we can also scale on 2 nodes. All right, we can see that already the one with 32 cores and 64 cores are finished. We can check the logs. So we'll check the output file of the job. So here it's really each of the individual worker writing logs, so we can see the number of the process. What we are interested in is a summary we get from once everything is done. So we see with 64 cores, it ran on at 54 seconds. What we are going to do is put all these times that we are going to obtain into an Excel. Always the idea is to get our graph of speed up. Sorry. And so we'll compute this graph. Okay, now we only have the small jobs still running. The big ones are done. Here you can see that on 16 cores, it took 137 seconds. We'll also add it to the Excel. Then on 32 cores, it's 81. All right, we can already get a bit of intuition about the scaling. We see that when we double the number of processes, we don't really divide by 2 the time. It's not too bad, but it's not. We already see we are far from the ideal case.
And I guess this is also something important, that it doesn't matter if you throw resources on a problem if it's not built well. So that is the lessons learned here. Even if I mean, yeah, you can throw the resources at anything, but if it does not optimize at the end, then you're doing it probably wrong. And you should actually only request what you need usually. So that's also like a best practice. You shouldn't over request resources just because you're not sure. Better have less and then rebuild than to request more and then.
Yeah, we'll go to the limit, still step by step. So here is on 8 individual nodes, each of them running the full CPU cores. Okay, they are all running. You can even try with 64 individual nodes, each with the full. Okay, finally, so here we can see that the last job, the statue is Q, the letter Q, which means queued. The other one with R, it means running. So all of them are running except the last one, because we wait for the others to finish so that it has some free space. Let's continue with our Excel. Let's check the logs. With 2 nodes. So now we go into several nodes. With 2 nodes, we get 13 seconds. Which is I didn't wait. Okay, I did a misfield. So let's add this 13 seconds, which is not too bad compared to the single core, to the single node. We are almost half of it. So the scaling is not really regular. Then with 4 nodes, still all the cores. We can already see the limit. We doubled the computing power, but we will only gain 1 second. And yeah, maybe now the small jobs are finished. Okay, the only remaining ones are the 1 and the 2. So with 4 cores, 1 single node, we are 394. So here we have the speed up chart. I will just put a figure in. I think it was, we should expect something like 1,000. This is what we're going to expect. We just feel the real value of for 1 single node, 1 single core, but we can already see how it is. And 16 nodes. I mean, we can see we are gaining some time, but the amount that we spend, because everything in your project, you get what we call a budget in computing hours. So if to gain a few seconds, you spend twice as much budget, it's not really worth it to do. And it's not energy efficient, of course. We can see that our big job is still queued. It didn't start. We can have a detailed look.
Yeah, and this is when you actually start using this. Then, from my lessons, if there is, so you, as you can see, it's a Linux, right? This kind of table. You have jobs that are running, that are not running, and if you have somewhere a P like pending or something, then be very careful. Sometimes you're just going to sit and wait and don't understand what's going on, but there's pending because you have requested too many resources, and it just doesn't run because it doesn't fit into the queue that you have requested to, or there is some other issue. So you need to be actually. This is from practical.
Yeah, that's really debugging. So why is my job not starting? So we can ask to QStat to get the detail of the job. Usually it's at the end. We can see insufficient amount of resources.
Exactly. Yes.
That's
very
as
common.
expected.
Yes.
Yeah.
But this takes time. So if you have never used this before, then you just need to be careful with this.
Because you need, if we look at the other ones, yeah. This one is still running.
Because when I talked about the fair share and queues, then it's not just one big queue, right, that has HPC. HPC has multiple queues. There is the queues have different priorities, different amount of resources that they can give and are available for. So if you build your job, the job script, the BBS script, in a way that you request more resources than are available in that queue, then you will have exactly this, that it will be pending and it will have not sufficient amount of resources or something else. So you need to also be aware of the queue and what are the limitations of that. So when you build the bash script to run this. But this is the same for any HPC. But again, if you do this practically, then, and if you have not done this before, then this is one of the first things that you will face. Then this much more, that there is also, well, we're showing like the threading and having a MPI. Then there is also a concept called, for instance, arrow jobs, right? So instead of having one job that is split into multiple ones, you can have multiple jobs that continue like an arrow, right? They continue each other. One input is one output is another's input. So there are different constructs that you can have to also optimize your code or project. But this is, again, something that you need to be aware of when you build things. And again, if you have never done this, then it might be at first difficult. And the general suggestion is that test with small resources and small jobs first, get some kind of estimate, and then actually do the real job. So that was exactly the question: how do I know how much wall time do I need, or how many CPUs? It's best not to over-request anything, and then just do the first test, and then you get either this kind of graph or something else, and then you can do an estimation and actually run this. Yeah.
We can have a look at the results. So in terms of storage, we have two different partitions. I think after we go back to the slides, we explain that you have the file system, that is, you have the project file system, and the Scratch file system. Scratch is for processing fast, but you're not supposed to keep files on the long term on this storage. So our results, you can see here, each job was writing the results here. So I mean, whichever we can choose. And it's all our tiles, so it's TIFF files, and we can see how they look like. We can use so it's the split. We use like 4th column, 6 row. We'll have a look at the results also, and also the inputs. So the first one was the output of the job. And here I'm just getting the input, and we will visualize it on the screen, just so that we have at least something concrete out of all of these jobs we have run.
Yes, otherwise it looks like a lot of a lot of scripting and no results.
So yeah, PAN is panchromatic, so the black and white images, and MS is a multispectral image. And the first one we got, the PMS, is the output, so the combination of PAN and multispectral. Here is a multispectral image. We can see the pixels, the panchromatic image. It's a bit dark, but we see it's a higher resolution. And finally, our output is this. So it's not a state-of-the-art algorithm we used. We use something, but there is really some research on this field, how to really merge in a correct way the panchromatic and the multispectral image. Okay, I think we can just check, go back to our project and check if all our jobs are finished. This one is stuck. I have no idea why. See, it's supposed to be fast because it's 32 nodes, but it's been running for 13 minutes. So maybe we'll have a look. The only one that is missing in our Excel is the one with 2 cores on a single node. All right, so I mean we could change the scale to have a more logarithmic scale, but already it's you can see how it goes. Quite quickly, we can try to stop at even starting from 16 or 32 cores. We see that the divergence between the ideal case and the reality of the speed up. Okay, I think we can go on. We will not wait for the jobs to finish. So we got something like this. Not really, we didn't get a drop in speed up, fortunately, because it's individual processing. We have bottlenecks, but it's not as bad as the example I showed on the screen. Now you've seen a bit of the HPC. Let us go back to the file system. I told you we have the project file system and the Scratch. The project is made, you put your code in it, you put your valuable data in it, and the Scratch is only a kind of temporary space to run your processing. And both are equally fast. It's just that the Scratch you have more space, and it's really made for it for being accessed by the jobs. Then something I showed quickly in our job submission was the module that we can use. In an HPC, it's really common to have modules, so you can independently load several software, and it will not interfere when you install them. So we can install a software, package it into a module, and user can use them by doing module. Well, first, they can have a look at which modules are available, see what is the description, how they have been packaged, what they encompass. You can show, but the most important one is module load. What you will use in your script. What we used, for example, is module load MPI, so that we can module use Python, module load Python, and like this you can use really the software you want. By default, you don't have anything loaded. You just load what you need. More commands. That's more part of our documentation to explain the modules. To go a bit deeper, you can purge everything, reset, replace, anything.
Maybe this much about the software, that when you build this kind of things, there are always dependencies, right? When you use, I don't know, Python, then quite often, especially if it's something that's been built for a long time, then there is these older libraries. Then you do need to be prepared to load them separately, right? So you need to make sure that all of the dependencies are correct versions. So again, lessons from practical implementations that you might get stuck in the middle of it when you have you have one version wrong somewhere, and it just crashes. So again, something that you could theoretically pre-test before you submit it, like the full job. But these kind of dependencies are quite fragile. And I guess this is how the job script then in general looks like, right?
Yes, that's the one we saw in the demo. So we can explain it line by line.
Yeah.
So the select is the core of what you are going to ask in terms of resources. So you specify a number, which is the number of nodes, and then for this number, you specify how many CPU cores you're going to use per node, how much memory, how many MPI processes you can run. You can do hyper-threading on your cores. And for the GPU partition, you can specify how many GPUs you want to use. And the queue, either you go on the CPU queue, which is you will get only CPU nodes, or the GPU or AI. This one as well, we saw them during the demo. You submit your job with QSub, then you can see how the jobs are going with QStat. You get the list. And we saw also with QStat, you can get details of one specific job to know what's happening with it. I think we can go back to a new demo, which is now using GPU. We will use deep learning. The use case, it's always Earth observation. It's going from Sentinel-2 images, so 10 meters resolution, to 5 meters resolution images. So the dataset, what we have in input is Sentinel-2 images, and in output is a satellite demonstrator called Venus at 5 meters. And the goal is to do artificial enhancement of the Sentinel-2 images to look like the Venus image. Still the same story. Really, that's something, if you want to take away message, is how do you parallelize anything? So we saw that on CPU we split the image in several pieces, and we do the same with deep learning, only that we split the dataset in several pieces. That's the second one, the data parallelism, and it's relatively easy to implement. Then the first one is the model parallelism. If you have a big model, you can also split your deep learning models across several GPUs, but really that's not easy. And for us, for our use case, we use relatively small model. It fits into the memory of one GPU, so we can use the second one, the data parallelism. Here is the dataset we use. There is an open source dataset, and the nice thing about it is it's already in PyTorch format. It's already split, and what we need to know when you use an HPC, you will not necessarily be able to port your code from your laptop to the HPC, because you need to have an optimized dataset, some optimized data loaders. And the nice thing about this PyTorch dataset is that it's optimized. It can really scale out and be efficient. If you use a basic image like the TIFF that we used for CPU processing, it will not scale at all well, because you will spend a lot of time reading files, doing stuff. With the PyTorch, you load them directly in PyTorch format, and each PyTorch contains multiple small samples. I think that's quite a rule of thumb that each of the files should be a few hundreds of megabytes. That's what we are using for the dataset. And now for the model itself and the training, we use also some open source thing we found, which is SR is a super resolution, and we do it takes into input the dataset we saw before, and it does some training around it with some already predefined model. So we are not AI engineers, so we just take what other people do for showcasing the HPC. And the nice thing about it, it's using PyTorch Lightning, which is a wrapper of PyTorch, an overlay of PyTorch, and it's already made for using different strategy of training. You can scale with this software. So here you see we have the dataset that is ready for scaling out. We have the software stack that is ready for scaling out. So it's not every dataset or every code that you can port to the HPC. You need to work a bit on it. So for us, it's been using the optimized dataset and using this PyTorch Lightning software stack. Okay, let's connect. Let's first look at the results of our single like this. We'll fill the Excel. Okay, it was quite close to the estimation. So already, only when doubling the CPU, we get already a 5% drop in performance. Then the 5% becomes 10%, and so on and so on. We can see it. So we are done with the CPU use case. Now let's move on to the GPU. As usual, you have a submit script to submit your workload. Here we ask for one node, 8 GPUs for 20 minutes.
Yeah, we don't have that much, but okay.
And here's the actual code, which is train.py. I show. Well, first I submit the job.
It seems so easy. You just click, queue submit, and the job runs. But it
Yeah.
actually costs a lot of money, right, to run this. So, and if you do things wrong, then things can go very bad. So,
Yeah, it's really consuming some electricity. You can have a look. By the way, we see the job is already running on AI001, so we can connect directly to the compute node. That's the only way to connect to a compute node, is to have a job running on it. I will do NVIDIA top. And zoom. We can see the 8 GPUs currently used. So it's a bit fluctuating, of course, because you load data, you process, you do one epoch, one iteration, then you go on. We can already see that our model is relatively small because we are using only 14 gigabytes of the GPU memory out of the 80 available. Here is a fancy graph. Then all the idea of the optimization is, of course, that when there is some processing, to reach 100% of the GPU utilization, but also to reduce you see the time that we go down to 0. That's part of the job you do. When you run on HPC, you need to optimize. And we are done already. Here we have our 2 logs, so the error and the output. I will not go too much into detail on it, but let's have a quick look. Still, have a look at this loss, which is the indicator of is the model well trained or not. The lowest, the best, the better. The lower, the better. So we started at 0.34, 0.28, 0.8. This step was not back at 9, 0.1, 0.1. I mean, let's not take too much time on the content. As I said, we're not here to do AI. We're here to showcase the HPC. But that's what we can do when you have optimized. And the output this model, which is trained on our dataset. So in the example, so that it runs quickly, I used a small dataset. I think I used like around 1% of the full dataset. So if we would run on the full dataset, it would take 100 times more on the 8 GPUs.
but we can still see that it works. So that's the important part.
Yes.
So in any case, it's always quite technical, right? So you look at this, but what is the result? But if you have again, going back to, if you have a use case, if you know exactly what you want to achieve, then it's quite often is exactly this number crunching and optimizing and trying to figure out. So it doesn't produce you usually this kind of nice output, except for maybe this one. But it does result in data that you wouldn't otherwise be able to get. So you really need to figure out what is the best use case and what exactly do you want to achieve.
Yeah, so now we are done with demos. If anyone has questions, feel free. on either on the HPC or anything. If you want us to try something else. Yes.
There was some other process displayed during the Q-step.
Yes.
Everybody see everybody's processes.
No, I'm admin. I can see.
No, yeah, but this is a fair question. In general, depending on what you do, the data and the information that you get from this might be confidential, right? So we,
Yeah, they say that it depends on the HPC. Some HPC enables you to see the full list of who is running, but for us we don't want this. So
and also when you actually request resources, then there is also questions on what is the, I guess, the confidentiality level and what you want to actually, be secretive about. So let's put it this way.
yeah,
so
we are currently in the certification process to get ESA classified information on the HPC. It's not done, but we would like it to be enabled, and these kind of things we don't want that other users can see what other users are doing, because of course it's a shared machine. It's the most efficient way to use resources, computing resources, but we share it, but only the compute nodes, only through the scheduler, and we really tighten what other users can see.
And this is also what is the difference, I guess. This is the entire philosophy and open source versus closed source. I mean, when there's a Slurm, which is open source, versus BBS that we are using, this is closed source. It's a bit different. So BBS is more of this kind of corporate, very strict and rigid kind of system in a way. So it kind of supports this layer of defense, I guess, around this. Someone else? Do we have anything else?
Yes.
You are going to open this for SMEs who have contracts with ESA. I represent one of those SMEs. But what could be the typical use cases for that? I mean, I don't do Earth observation. What would be typical use cases for SMEs in Europe who are using this?
Any SME that wants to do model training, not only Earth observation, now you have LLMs, of course. Anything, it can be really anything that needs deep learning, that needs AI. And then the CPU part is for more traditional space workloads. So I told you about mechanism, fluid dynamics, simulation. This will run on the CPU. I mean, even some startup, not all startups do AI, so it will be useful also for them. I don't know about you, if
Well, we design electronics for satellites, and one of the things I'm the head of marketing. I know nothing about all this stuff, but I can imagine that I want to run animations for commercial purposes. Is that a use case? Could I do that?
yeah, it could be, but maybe the HPC is a bit an overkill for it. But yeah, you could.
If I go back a bit on time, then a few years back, let's say 4 years back, there was this buzzword, digital twins. I don't know if you remember. Everywhere there was digital twins, right? Now there is AI. So all of these things are actually supported for HPC. HPC is at the end a tool. It's a big computer that does things quickly for you. And depending on what your need, I mean, yeah, for SMEs, I guess any kind of problem solving, I would still, yeah, AI is very, I mean, it's a popular thing, but it's not something that everybody does. But digital twins, smart engineering, and all of these things, I mean, you would need HPC for these things. So, and there's also a lot of data that ESA produces that could be used. Just saying, just have a look. It's not utilized fully, so you could take the data and maybe get a business case out of it. So, yeah.
Yes.
If you're talking about commercial use, do you really mean that the company could use it to sell a service to their clients?
Yeah. I mean, the idea is to enable SMEs or any industry to do innovation and to develop their product. It's not a open source license. Anyone does whatever they want. The outcome of what they do on the HPC, it's theirs.
So you don't differentiate between the research and development part and directly selling something?
No, for us it doesn't matter. We provide the resources, the access, and then
Usually do have a contract with ESA. It's all written there what you do and what you not do. So, but that is a major difference between the other HPCs that are available. So if you take, for instance, the process of getting access to the Euro HPC, right? It's horrible. It's the amount of effort that you need to do and justification. It's very difficult. So one of the aims was for the Space HPC was to make it easier a bit.
indeed for your HPC you may need to publish the results or your things. For us, it's not a research HPC. It's a research and development and innovation HPC. So we are not tied to research at all.
So I guess there would be a lot more that we could talk about from my notes. For instance, the difference between MPI and Open MPI, to all of the what is the ranking and what are chunks. But I guess this is more something that is extremely technical, and we don't need to discuss this. So my suggestion is that if there's no more questions, then we can have an early lunch. If that's okay, unless somebody has questions. Good. Guess we can end this then.
Thank you.